Hi everyone, I'm George Nakayama. I will be presenting DiffFacto, controllable part-based 3D point cloud generation with cross-diffusion. With the growing demand to create rich 3D contents, we seek to design an efficient tool to facilitate the otherwise laborious creation process. To allow users to bring their ideas to reality, the creation tool needs to be user-controllable. For example, a user may want to put a lamp on a desk or a suitable chair on the beach. Motivated by this observation, the goal is to design a shape generation network with multiple intuitive knobs. Specifically, we want the ability to independently sample different parts of the shape and coherent part configurations of the same shapes. Previous works have either focused on 3D generation or editing separately. Works like Lion encode shapes as a global shapecode. At inference time, it can only perform unconditional generation without control. The other lines of work, such as Spaghetti, focus on shape editing alone. However, they cannot generate novel shapes from scratch. In contrast, we introduced DiffFacto, a novel probabilistic generative model that enables both generation and editing tasks. To achieve this, we propose a factorization that decomposes the shape space into the individual part styles and their transformations, where these factors are sampled and encoded independently. We also assume independence on the part styles and conditional independence on their transformations. To train the model with this novel probabilistic factorization, we variationally maximize the evidence lower bound. This results in 3 terms, with each term corresponds to one major component in our network. The first component are the part stylizers, which model independent part style latent distributions using independent normalizing flows. Given the set of part style latents, we design a transformation sampler that models the distribution of transformations using CMLE, which can model multimodal distributions. This benefits the transformation sampler because there are many valid part transformations given a set of part styles. Lastly, to produce coherent shapes, we design a cross-diffusion network that models the shape distribution as a joint of part styles and transformation. To generate shapes, it uses probabilistic diffusion model with a modified forward kernel. During the forward path, the shape gradually diffuses into a transformed Gaussian according to the sampled part transformation, only destroying the local high-frequency details during the process. We empirically observe better extrapolation and reconstruction quality compared to the vanilla diffusion kernel. Our model enables many editing and generation applications. By sampling different part style latents, our model is able to generate shapes with controllable parts. The figure shows generated shapes from different categories with the gray part kept fixed. Quantitative metrics also shows better performance against existing baselines because of our novel factorization. DiffFacto can also generate shapes with different part configuration. On the left, we see samples of different part configurations for different categories. We also ablate our transformation sampler, and we see that our choice of leveraging CMLE outperforms the baselines both qualitatively and quantitatively, thanks for its ability to model multimodal distributions. By encoding parts from different shapes, DiffFacto is able to mix and match them together. We compare with the control-enabled baselines that do not disentangle part style and transformation. Because of size mismatches, the baselines fail to produce coherent shapes. Moreover, we can also produce size variations of the mixed shape from our transformation sampler. DiffFacto is able to perform part-level interpolation by interpolating part style latents. Because we disentangle part style and part transformations, we obtain covariant changes in unreferenced part size. Moreover, because we model a smooth part style latent distribution for each part, we obtain distinctive geometrical transition during interpolation. Lastly, with DiffFacto's ability to controllably generate shapes, we can use it to improve downstream tasks such as semantic segmentation. For example, with a pre-trained segmenter in DiffFacto, we can augment the original dataset by selectively sample a few shapes from DiffFacto. With only 9% of data augmentation, we are able to improve the mean IOE by 11% relative to the segmenter trained only with the original data. Thanks for listening.